Little intro, guys, to the reduction of linear forms in this section. There's 10 questions here. How to reduce equations to linear form. So if you've got equations that look vaguely similar to this, for example, I've listed 3 typical examples here. And suppose we have some data points. Well, these are non-linear curves, aren't they? And it's very difficult to fit and work out the values of the associated constants. But if we can transform this in some way by using algebraic rules, and transform this into an equation that looks like it's in linear form, and then we can plot the coordinates that arise from transforming this, then we should have a series of points that we can mark off an x-y axis, which we can then find m and c, the gradient, and see by just drawing a line of best fit. So we'd end up with an axis, we'd have some points that we'd then be able to plot. We could draw a straight line, best fit through them, and we could work out the gradient, just the slope of the line and the intercept. This would give us capital M and capital C. And then once we've got that, we can transfer it back, go back to the original problem, because we would then be able to determine the unknowns A and B, say, or A and N, or A and B here. So it's best explained by examples. So if we look at the very first example then, so if you've got y squared equals ax plus b, I've done it here. If we compare this to a straight line form, what we can see we'd need to plot is we'd need to plot these points here, the x values against the y squared values, and then that will generate, once we plot those points, so if we've got some coordinates like this, we just need to, well, the x1s are okay, so they would be the x coordinates, wouldn't they? But we'd need to square each of the y coordinates. And then we get these series of sequence of plots that arise. We could then plot them, these points, we plot x against y squared. We'd then plot them and see if there's a linear relationship. And if there looks like there's a linear relationship, we can draw a line of best fit. We could then find out m by just measuring off the gradient, and we can measure c, the intercept. Now in this correspondence, once we've got m and c, we can work our way back to the original equation, can't we? Because the correspondences are all laid out. So here you can see that m is none other than a, and capital C is none other than b. So once you've got m and c, it won't be quite so simple most times. You'll be able to work back and get the values of the value here, say, for example, and here, and get the original relationship, if such a relationship exists. So what we're going to do in this section, we won't focus on the actual working out gradients and intercepts, because it's very straightforward, and then plotting points that arise when you manipulate the data into another form, and plot data and then get m and c and work our way back. We're not going to do all that. All we're going to focus our attention on is how do you go from an equation that looks like this to translating it or reducing it to an equation that is linear in form. So if we get that under our belts, then this mechanical process should follow naturally once we see the gist of how to do this process. So there's 10 questions in this section then, guys. All the best with it, and I'll catch you in another section. Cheers!